Good morning, everyone. Good morning, Abhinandan. So participants are still joining. We'll wait for another 2 to 3 minutes and then we'll start with the session. And before that, I have few announcements for the participants. The first thing is that, as you all know, as per the schedule, today we are having a second MCQ for this particular program. The quiz is scheduled from 2 p.m. So request you all to kindly be present and be active for the quiz during that period. So the quiz will end by 2:30 and you have to ensure that you submit the quiz within the allotted time, as there will be no auto submission button. And also note that you can attempt the quiz only once. So once you have submitted, you won't be able to submit the quiz again. And the second announcement is that, so as you all know, the materials for day wise, all the materials are being uploaded on Drive, as well as your attendance are being updated on daily basis. So a request to all of you to please keep checking your attendance, because if you have any query regarding your attendance, so you can let us know immediately in the Telegram group. For any query related to attendance, you have to post in a Telegram group. Please do not post in the chat box in the WebEx platform, as it creates disturbance for the expert, for the speaker. So this is a two announcement, and other thing is that always keep checking the Drive folder on regular basis, because any important information, it's always posted on the Drive folder. Either it be material, either it be quiz link, or any important announcement. Everything are always posted on the Drive folder. So please make a good habit of checking the Drive folder on daily basis. So I'll repeat the announcements once again. The first thing is that you are having your first MCQ session, second MCQ today from 2 to 2:30 p.m. You have to ensure that you be present during that period. You can find the quiz link in the Drive folder. The quiz link will not be shared separately either in the WebEx platform or in the Telegram group. You have to take the quiz link from the Drive folder itself, and you have to ensure that you click on the submit button before the allotted time, because the same quiz will not be reopened again. So try not to miss the quiz within the allotted period. The second thing is that you have to keep checking your Drive folder on regular basis. Your materials and your attendance are updated on daily basis. So if you have any query related to those things, please post in the Telegram group, not in the WebEx platform, as it creates a disturbance for the speaker, because the speaker always looks for the queries which is related to the topics being taken up at that period. So thank you, and I welcome you all to the 8th day of this program. I hope you all are enjoying it. So today's session we have will be taken by Mr. Luke Kenan Casson-Lington. So, but because of some time constraint, he will not be able to physically be present in the platform. So, but he has like coordinated with our Abhinandan sir to ensure that his sessions are being taken up like without any problem. So Mr. Abhinandan sir will be coordinating with him for delivering the session. I'll just give a brief introduction of Luke Linton sir. Mr. Luke Cannon Castle-Linton specializes in ethical technology. He has been using programming and reverse engineering computing devices continuously for 44 years. Uh, has has a Bachelor of Engineering honors ACGI in Theory of Computing from Imperial College, and recently put that education to good use in the form of Libre Associate Project, an entirely Libre licensed 3D hybrid CPU, VPU, GPU based on OpenPower. He writes poetry and has been developing a HEP physics theory for the past 36 years in his spare time. So this is a small introduction of Lute Lincoln, sir. And we have with us Mr. Abhinandan, sir.
Yeah, ma'am. Thank you. Thank you. Let me share the video.
Yes, sir. So Dr. Abhinandan is the associate professor at NIE Mysore and also an IBM power champion. So over to you, Abhinandan, sir.
Yeah, thank you.
Yeah, thank you.
I hope participant can see the screen. So let me play that.
Lecture on. Hello.
Yes.
So, and other thing, if you have questions, right? Can you actually make a can you collect and send it to me so that I will forward it to Luke and then I will share it back to you, ma'am? Is that fine?
Yeah, sure, sir. You sure? So
Plus, whatever the comments that they actually, what are the queries that they have, right? If you can actually collect it and then send it to me, so that I will actually work with Luke and get it resolved and get it and send it to you, ma'am.
sure, sir. Yeah. So
Because I'm not
participants.
expert on this topic, so obviously there will be a lot of questions, and this is the way where we can address. So probably if you send it to me today, then I can follow up with the team and get it as soon as resolved. Okay.
Sure,
I
sir.
hope
Sure.
you can listen to the audio and you can see the video, right?
So the video is there. So just play the video once so that we can confirm if the audio and video is working fine.
Welcome to a lecture on the LibreSoc project, and the core of this material will cover the differences between developing something for an FPGA and developing it for an ASIC.
Ma'am, can you hear? Is that fine?
Yes, sir. It's audible at my end. So participants, I would request you to kindly post in a chat box if you are, if the audio is clear at your end.
Yeah, and also I can share the YouTube link for this video also. So after
Yeah,
this, I will share so that the participants can actually uh, uh, can actually listen also. It is actually uploaded in YouTube also for this reason. Yeah, let me continue playing.
So the same lectures are also being streamed on YouTube. So they have the YouTube link, so they can keep visiting, can see the session.
Yeah, sure, ma'am. Yeah, ma'am.
Yeah, audible. So someone is said is not much clear. Anjan Kumar sir said it's audible, it's good, and Tejashvi Danda said that not much clear. So other participants are also request, so please post your views if the audio is clear at your end. We just received only 2 response from the participants end. We are having around 200 participants join with us. Other participants, please post your views if the audible was clear at your end. Not clear.
Okay. Yeah.
Clear. Someone is saying it as clear and someone it's clear. It's maximum are saying it to be clear.
Yeah, ma'am, we'll go through it, and then I would after this session I would actually share. Probably I will write it in the chat box about that YouTube link so that the participants can actually go through it. The original YouTube link also, because we have uploaded it in multiple multiple venues, especially on YouTube for this reason.
Sure, sir. Sure.
Yeah, thank you.
Thank you, sir.
And how to go about being able to target both. We can also target simulations in several different ways, but that's out of scope for this particular course. So A bit of background, this is our project. It's our main website. It's a wiki. It's editable. We're a Libra project. Okay, and that has very specific meanings. It means that the majority of open projects, they will throw the code only when it's ready and when it's done. Libra, everything is transparent. We make all source code, all technical discussions about that source code are entirely public and real time. Also, there are ethical guarantees behind Libra where open is considered unethical because there is no requirement that people who use it actually contribute back the modifications and enhancements that they need to do, whereas Libra requires that you contribute back those modifications. So on the sidebar here, you can see that there is a number of resources, including our charter, links to the mailing list and archives, etc., etc. Now, let's go first of all over the LibreSoft core itself, and then expand out from there. So what we have is we are running a very simple finite state machine. It is not a pipelined design. And the reason for this is because it can be used as an exercise, an academic exercise, because it's very straightforward and easy to see how it works. When you get into pipelining, it becomes extremely complex. The overlaps, just you have to know a lot about the internals, etc., etc. So what we did was we went through the standard fetch, decode, issue, and execute phases, but did so one cycle at a time. So pipelines, they will run them, that run all of those in overlaps, whereas this, it does a fetch stage, waits for that to complete, then passes the instruction that is fetched to decode phase, waits for that to complete. On decode, it's been able to identify what the instruction is, so that it can then read the registers that are needed here. It then passes those to a pipeline. Now we have multiple satellite pipelines. There's not just one pipeline in LibreSoft design. There's actually 12 separate pipelines because we're planning ahead for an advanced design. And again, it waits for the execution to complete, and then that's followed up by writing the results to register files. And then in an intrusive fashion, what we do is we detect if the program counter was written to by the previous insert, by one of the pipelines, and if it was not written to, then the issuer finite state machine will increment the program counter and store that in the register file, but it also sets the MSR register, which is part of the power instruction set. And there is a separate pipeline finite state machine for updating the DEC and the TB register, which are timer and decrement registers. Now, and then it goes back and does it all again. Now, a little bit more detail going over that thing. The program going to fetch phase of the finite state machine will fetch over the instruction wishbone bus. Okay. At the decode phase, we have a class, a Python class called Power Decoder 2. By the way, all of this is written in NIMIGen. NIMIGen outputs Verilog. There's a very specific reason for doing it that way and using NIMIGen rather than Verilog, because Verilog is 1990s technology. You cannot do classes, you cannot do properly do interfaces, and it creates unwieldy, unmanageable code. We therefore consider Verilog to be a machine code target. Right, and that's how the NIMIGEN works. So the Power Decoder 2 will actually decode the binary instruction, but it also receives the interrupt lines, external interrupt and other interrupt sources. And on the basis that when a interrupt occurs, you need to execute an interrupt. You need to carry out changes to the program counter. You need to thing, and it turns out that this is basically the equivalent to trap. So what we've done is, in a microcode form, is simply left the overloaded the trap mechanism to make it look like we're executing an instruction, and that instruction updates and replaces the program counter of the MSR and stores the old copies of those in SRR0 and SRR1. Right? But it's done by getting the power decoder to go, oh, there was an interrupt. I'm going to ignore the current instruction that came in for the decode phase. I'm going to issue a trap instruction, aka interrupt micro-coded instruction instead. Then, having decoded that instruction, you go for you can know what registers would need to be read, and we have a lot of separate register files: integer condition register, SPR slow, state fast, and a fast SPR register file, which is very, very small and has massive number of write ports, read and write ports. But it's very small, and it contains link register, tar register, a couple of others, which are needed for high speed access. And there's a separate XER register, and that's merged into the SPRs when it's read. And Microwatt does exactly the same thing here. So having read all the registers, then go into the pipeline execute phase. Now here what we've got, because we have multiple pipelines, we also have multiple satellite powered decoder 2 instances. And these, thanks to using Python, we can subset those by the fields that are needed in the columns and subdivide them for the rows, because at the back here is the main decoder. The main decoder decodes every instruction, but it only decodes enough information on how to identify the registers to be read, the register to be write, and the pipeline to which the instructions should be farmed. Now, that leaves more information in the instruction which needs to be decoded, but it could be done in a satellite form at the source just right before the actual instruction. So standard pipeline thing, the instruction goes to it, blah, blah, blah. You get a notification back that the output is available, and that goes into the register write thing. Again, it's the same, exactly the same as the read reg files. It's the same thing. Right? Now, I'll show you the source code for this later and link to it. Now, in addition to that, in the same class, there is a debug DMI interface, which is mirrored on the RISC-V DMI concept and conforms to the same API. But it's actually implemented in Microwatt. Microwatt decided to do their own DMI addressing system, so we just copied that and we're fully compatible with it. Now, this manages the core, and it's fronted by a JTAG tap interface. So there's an adapter from JTAG to debug, which is not part of the actual core itself, but it's just a front. And through the DMI interface, what the Micro team did was they defined some registers so that when you poke the particular address, it means it gives you some bits which indicate please start, or please stop, or please reset the core. So over that interface, we could send commands, and because it's linked to JTAG, we can send JTAG commands to start, stop, and reset the core. And that hooks into the finite state machine here. So you send the command over DMI, and it acknowledges immediately. But of course, you cut the finite state machine. The actual execution is in the middle of executing things, so it can only just, what you have to do is wait. You get some information back, which you have to make another DMI request to say, have you stopped? What is your status? And you'll be able to check it if it's stopping and if it's stopped. Right. So again, over this DMI interface, you've got PC update and read, and you have register read. So you have yet more ports into the reg files here. The one thing that I've missed to say is that the load to store pipeline is what accesses the wishbone data bus. Okay, right. So there's these two wishbone masters. One is the instruction wishbone master and the data wishbone master. But the actual core itself does not get involved at all with load store accesses. It's handled entirely right down at the end of the pipeline. So with that in mind is what the actual core is, we can now move to where the interface is. Here's what the contents of that previous slide was with the previous diagram was with the test issuer. So you can see the instruction wishbone bus is input and output from it. The data wishbone master is on here. We have some interrupt lines coming in, which go into the ZIX controller, which has a ICP presentation layer, interrupt controller presentation, and interrupt controller session layer. But it becomes a definition of what the interfaces are for test issuer. And we have the DMI interface, right? So then there's also those pipelines and registers, and also the actual decoders, the main decoder and the satellite decoder. So as far as everything else is concerned, you see basically these four sets of wires: the DMI, which includes everything for JTAG, the interrupts, and the wishbone bus. You see nothing else, literally nothing else. You don't see the registers because that's handled through the DMI. You don't see any pipelines or anything like that. So there's just these four interfaces. Now, on the other side, we have the JTAG tab. Right. Now this is a standard 4-pin interface, and what Chips4 Makers has designed into the JTAG tap interface on NITJ, written in NITJ, is the ability to add a wishbone master. We also added the ability to add a DMI interface, and there's also a standard boundary scan system. Right. Now, most FPGA open source code does not have boundary scan. Why would you need it? And the reason why you won't need it is because you can very simply reconfigure your FPGA bit stream to use different pins. You just recompile the bit stream. Right, so this becomes one of the key differences between FPGA programming for FPGA and programming for ASICs. You have no idea if when you have an error. One of the crucial things to understand is that you need when you have a bug and you've basically got a black box. The last thing you want is more than one thing that could possibly be a failure. And the reason for that is because if you make a test where that test is a single thing, success or fail, if there are two possible things that could have failed, you have four possible permutations, only one of which you can dictate when you get your black box outside success. One of those permutations will be because of the two failures, because of the two things. The other three possible permutations, you have no idea which one of those two things caused the failure. And so let us say that you have a failure in the core and you have a failure in the I/O pad. From the outside, you cannot get access through the JTAG interface to determine, my iPad, I'm not getting response on this I/O pad. Why is that? Well, you don't know. It could be a failure in the core. It could be a failure in the I/O pad, and you cannot tell which it is. So by having a boundary scan and separating, you see this break here, you cut the entire core out of the equation and go directly to the I/O pads. And by going directly to the I/O pads, you are able to determine if it is the actual I/O pad. And then, if that succeeds, then you go back to enabling the core, and you can, by logical deduction, if there is a fault and the I/O pads are okay, you know it was the core. But unless you have this, the ability to directly test this one and one only one thing, you cannot determine which one it was. So so that's why why you have boundary scan. Now the reason why you don't have boundary scan in FPGAs is because you don't need it. You can just reprogram the FPGA to route the peripheral directly to the pads. And if it's not the right thing that you need at that particular time, just go back to the source code, reconfigure the source code, recompile the bit stream to connect different peripherals, and upload the new bit stream to the FPGA. Clearly, you cannot do that in an ASIC. So LITEX is actually configured. It's not configured to understand this concept because it has been designed exclusively for FPGAs. Consequently, we had to do a lot of hacking to get it to understand this the separation between the two, and I'll go over that later on. So whilst LITEX itself defines the peripherals, which by the way are nothing to do with the core itself. Core is just, it does memory access only. It's memory map peripherals. So this is why you have to have memory map peripherals, because the only interfaces that the core understands is via memory and interrupts. Okay. So consequently, the peripherals must define their public interface as far as the core is concerned in terms of memory and interrupts. And on the other side will be the I/O pads that come out. So in the test chip LS180, we wanted to include SPI I2C, UART SDMMC, SDRAM, which is DDR1, is 133 megahertz DDR1, GPIO, external interrupted PWM. But it turned out that we had too many resources, I think, so we cut out many of these, but kept E&ICT, GPIO, SDRAM, UART, I2C, and one SPI master. Now, what they would then have to do is route those. So LITEX defines a set of pads that are normally connected directly to the FPGA resources, internal resources. We had to route those to the JTAG tab boundary scan. And the JTAG tab boundary scan to do a MUX switch that then either routes to the through to some internal registers, which you can read or write to via JTAG. Or if you flip the switch, the MUX reroutes it to the actual I/O pads that would normally LITEX would connect directly to itself. Now, this a minor complication is that those the JTAG tap code is actually inside test issuer as one of its submodules. So for convenience, what I've done is I've written this diagram out in such a way that it appears it's not quite the case that, but is this component here is actually inside here. And what that means is that every single pin on here, defined by LITEX, has to be on the public interface here, but it is not part of the actual core itself. The core only understands memory, wishbone, and interrupts. Okay? So let's move on to what some of the differences are when you have between an FPGA and an ASIC. In any ASIC, you have LUT4s or sometimes LUT6s, and these are lookup tables, which have 4 inputs that can, depending on the permutations of the inputs, it will create via a lookup table, hence LUT, a combination of outputs. So if you have 4 inputs, you have a 16-entry state table, which creates, based on any of those possible combinations of the 4 inputs, will produce outputs. And this basically allows you to emulate, and I do mean emulate, XOR gates, MUX gates, NOT gates, NAND gates, AND gates, blah, 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 all the standard gate things. Now, one thing that LUT4s can't do is they can't be a BRAM, block RAM. You also have DFFs, which are latches, and typically the more advanced FPGAs will also have a DSP. Right, and the DSP will have multiply and add, etc., because to implement multiply is a massive number of gates, and it's just a waste of resources, waste of LUT4s. You're better off doing it in a very efficient manner as a dedicated DSP block. And then you have GPIO of different types. Now, here we have one of the key things. GPIO. You basically reconfigurable GPIO. You have to have an input, you have to have an output, and you have to have an output enable. Now, I won't go into the differences about things like DDR pads and SerDes differential pair pads. Basically, they're exactly the same. They have an input and they have an output, and they have an output enable. And when you raise the output enable high, the pad becomes an output. When you raise it low, it becomes an input, right? So here's the LibreSoft core, and it's separate from that is the LITEX peripheral generator, and the whole lot gets compiled to Verilog. There's one Verilog file for LibreSoft, one Verilog for LITEX peripherals. They get thrown to the tools, and the tools generate the cells and the resources, generates a bitstream which will conform to the things and do everything that's needed. And that's handled by LITEX, but there's several other tools as well. NAMIGen itself can actually target a huge number of FPGAs with the different platforms on which those appear. Now, and also in the FPGA you have PLL block. Okay, now in an ASIC you get no assistance of any kind from any resources. You have to do everything yourself, right? So you have to have a PLL block, you have to have SRAM blocks, you have to have MUX blocks, you have to have a flip-flop block, a XOR block, a NAND block, a NOT block, a buffer block, a diode, everything. And these are called cells. And don't be confused by the term cell. It means any collection of gates. So there is even a LibreSoc cell, and it's 130,000 other cells which are laid out in gate level. There is a PLL cell, and that's about 10,000 transistors. I think comprising some other cells. So please don't be confused when you see the concept of cell referring to something that's only got 5 transistors, and the exact same term referring to something that's got 500,000 or 1,000,000 transistors in it. Welcome to ASIC industry, ASIC VLSI industry. So there is also an IO pad cell, all right, which has to be provided. Now, these are usually provided by the foundry, and the foundry puts you under NDA, which from an academic perspective prevents you and prohibits you from even being able to publish academic papers. Right, because you use some NDA material, you are prevented and prohibited from publishing. Isn't that wonderful? So this is why there is a huge amount of interest in NDA-free cell libraries and in NDA-free foundry process, in particular MOSIS. But MOSIS comes with some punishment in that it is double the size of the optimized cells that are non-NDA free, and only some foundries will refuse to accept MOSIS formatted GDS2 files. So you have to be, you know, it's a tiptoeing nightmare, to be honest. One of the key things, so we have to have a PLL, we have to have an SRAM block, or SRAM blocks, but you know, for register files, for onboard memory, and all these cell libraries. Now, we've I won't go into detail on that thing, but basically here you have all the resources on the FPGA side. You have all of these resources already done for you. Your LUT4s, your BRAMs, etc. They're already laid out. And the FPGA, you are allowed to route that pre-existing fabric, but through the bitstream. The bitstream gets uploaded and programs that routing. It's incredibly expensive in both area and power consumption, but it's reprogrammable. Whereas for the ASIC tools will actually lay out, and then you go and print it out, and you cannot change it after it's laid out, unless it's actually unless your ASIC is an implementation of an FPGA. It's quite funny. Now, the in, out, and output enable here, which in LITEX it gets connected as just a GPIO. Here, that triplet of in, out, and output enable per pin on your interface need to be passed right the way through the entire source code, entire netlist, until they hit the individual pad, IO cell, containing that in, out, and output enable. Right? And this makes for a very crucial thing, which LITEX doesn't actually support this, and we have to hack it into submission to get it to do so. In addition to that, we had to define a platform which had its own PLL, but as a black box cell. And likewise, the SRAM. So in LITEX, if you have a look at the platform, the things, the LITEX platform code defines and understands the PLL block and wires it up for you, so that when the bitstream is programmed, it will go into the it will enable and connect everything up. But here, because it's a PLL block, we need a .v file, which a Verilog module, which represents that, and LITEX needs to doesn't so much need to know about it as the LibreServ code just needs to tell the VLSI tools about it as yet another cell. But in this particular case, because it was defined externally by a LIB6 team, and because Yosis doesn't understand it, we actually had to mark that PLL cell as a black box to Yosis to get it to not try and do some optimization, etc., etc. And likewise for the 4K SRAM, which we put 4 down. So you won't see a 4K SRAM in the FPGA, and you won't see a LibreSoft PLL in the FPGA, because we are using the existing PLL and the existing block RAM of the FPGA resources. Okay. So this is why LITEX here we couldn't, because of the JTAG boundary scan, we actually had to route the peripheral set out of LITEX into LibreSoft. LibreSoft handled the JTAG boundary scan muxing, and then route it back into LITEX, and for LITEX to go and create the pin set. Remember, there's triple pad in and out and output enable for every single one of the pins. And finally, that will be passed to those parafiles. One of the LibreSoft.v and the LITEX LITEX.v will be passed to the VLSI tools. So here's the workflow. I apologize, I've missed off the PLL.v and the 4K SRAM blackbox.v files. So at the top here, you've got the test issue, you've got JTAG tab with its JTAG tab interface with the DMI interface and the ZIX controller. That is then, because that is in NMEGEN, it is handed to NMEGEN compiler. NMEGEN compiles that to a Yosis RTLIL file, aka ILAC file, intermediary language. Yosis then picks that back up and reads it in and converts it to Verilog, then saves it. And this is all under the control of NMEGEN. NMEGEN then saves that as a Verilog file, which we chose to call ls180.v. On the other side, you then run another makecar command, which runs LITEX to auto-generate the LITEX peripheral fabric interconnect, and that our use of LITEX is told it about the various interfaces, which we'll go over the source code in a bit, and that will generate a LibreSoft.v file again in Verilog. Now those two files are then handed through. So if you to the different workflow toolchain. So if you want to do FPGA, you run one command to build the FPGA bitstream, and if on the other hand, if you want to compile it to a GDS2 file, you hand it over to Coriolis2. Now, so let's say we go the FPGA route. We take the two Verilog files, ls180.v and LibreSoft.v, and through the LITEX command line, behind the scenes it will run Yosis to read those two files in and convert most likely to a BLIF file or an ILAC file. And then it will run next PNR ECP5. Now, YOSIS is actually pre-programmed, built in to understand the ECP5 cell structure. These things here: how many LUT4s, how many BRAMs, how many DSP multiply slices, how much GPIO, where is it, what is it, how many PLLs it has, etc., etc. And so when NextPNR receives the information about instructions, it will do a place and route, NextPNR place and route, and generate a bit stream. And that bit stream can then be uploaded to ECP5, and you've got a representation of your HDL, which actually runs at the gate on your FPGA. Taking the same route, going back to the ASIC, again, interestingly, it uses YOSIS thing. This time it compiles to BLIF, and it is at this point. Remember that YOSIS doesn't necessarily know about the geometry and the cell library, what the cells actually have. So you have to tell it. And in our case, what we've done is there's a couple of routes, but basically they both go something called FlexLib, which is by chips for makers, which contains the cells. And YOSIS is intelligent and general enough that when it's given those cells and told what the inputs and outputs are, it can actually do the mapping. It doesn't matter if you have a MUX4 or a MUX8 or a LUT4 or a LUT6 or a LUT8 or a buffer with this many. It's absolutely brilliant. It will just map your HDL down onto those cells. It's a cell mapper where a standard cell library happens to be a list of cells. So that outputs a BLIF file, which Leos and Coriolis 2 have been programmed to understand and read. Now, what Coriolis is it actually understands its internal data structures. It uses a subset of VHDL. So there is a BLF2 VHD converter, which then it can be picked up again by the place and route program, which is controlled under the control of Python programs settings.py and dodesign.py as part of Coriolis 2. After the place and route, which takes over an hour to 90 minutes, you end up with a netlist, which again you can extract and end up with this VLL subset, but it will be at the gate level, or cell level of connections to the cells, and consequently that cell library is an important input into this phase here, which is where you pick up the logical representations of the cell library in either Verilog and it's Verilog or VHDL, and it's why you have those. So it will also will output a SPICE model, a SPICE netlist with the same thing. So it's really very, very convenient, and you get the GDS2 file. GDS2 file you send off to the foundry, and you get your chip back. Now, one thing I didn't mention here is that the LibreSoft 180 PenMux is a crucial strategic part of this system. It's related to the peripherals. It actually ties in 3 or possibly even 4 different ways, and it's basically I'm slightly shocked and taken aback that in the standard industry practice you duplicate all of this information, but as a software engineer that's completely insane. If you don't have an automated way to represent the pins of your peripherals, you end up duplicating that information. You make mistakes. You can potentially make mistakes. And if you want to make even one single change, which we actually did for the 180 nanometer layout, because we needed to move the power pads, You need to make changes in 4 separate places, but data going right back into your HDL and into the LiteX peripherals and into the corona of the ASIC. So to avoid that insanity, what we did was we got this program, PinMux program, which auto-generates a JSON file, which every single one of these separate components, the Median HDL, the LiteX peripherals, and the Coriolis 2 Corona generator can pick up and understand, right? Incidentally, you can also generate markdown files from the same output, and even we chose to generate a where is it? I'm jumping ahead here. Yes, here we go. We chose this diagram is auto-generated. I did not write this by hand. All of those pads on the output and the input were put on through a Python program which outputted an SVG diagram. Okay? That's the kind of thing that a software engineer would do, but a hardware engineer would not, because hardware engineers are not trained in software engineering techniques. So I'm just going to pause the recording now and bring something on screen extra, because I wanted to show you the differences between when you run Yosis on some HDL for an FPGA and when you run it for ASIC. So please let me just go off screen and pause this, and I'll be back in a second. Okay. So this is a diagram which a partitioned signal module which we're developing for LibreSoft to do automatic SIMD, and this is a Yosis show top command on one of the test benches, and you can see we've got modules here for there's a greater than or equal test. As part of it, etc. And we can, if I do an additional command, show EQ_2, and we can see that this is doing a partitioned equal, right? And there's another submodule here, greater than thing, right? Now, so bear in mind that these are high-level connections. This is a net list for the design. Show top. Now what we're going to do is we're going to do a synth ECP5 return and show top. Yeah. Whoops, it's a big design, so it takes quite a lot. And here we go, and let's zoom in. Okay, so there's an output thing. These, I believe, are some of the LUT4 cells. Oh no, here we go. Here's your LUT4 cells. All right, okay. So it's turned it into a series of resources because Yosis contains an understanding built into the actual source code of Yosis, the lattice ECP5 cells, which we described on the other on the previous diagrams, the LUT4s, BRAMs, PLL things, MUX, DSFP, MOL slice, etc., things. So that's what you end up with there. So let's now load that in again. Yosis, read idling that file, proc synth. So show top again. Let's have a look at that. Let's do also, we're back to that top level design there. And now I'm going to run proc and synth. No, I'm not going to do that. I'm going to do read ilang and just plain synth. Now this will use a default standard cell library. And it's taking forever. Show. Okay, it's finished and it's done. Right, I didn't do flatten, so it will do it as show top. It will it will do as a series of submodules. So I will need to do show add _1. And here we go. Because I used the standard cell library, it's now, instead of LUT4 and etc., it's assumed that we're using AND cells. And here's a MUX cell. So there's an AND, a NAND gate, an exclusive NOR cell, an OR cell, and so on and so forth. And so coming back to here, that's what we do is we hand it the FlexLib cell library, which contains the cells that have been designed by chips for makers, and those the Coriolis IOSIS will then incorporate that and generate the BLF file from that cell library. Right? So it's quite it's really quite straightforward, but it's just that normally this cell library would be under NDA. You would not be permitted access to it, or you'd not be able to publish any academic work having signed such an NDA, which is accepted at a very high level. And consequently, there's been something called Free PDK 45 has been designed, which FlexLib has been ported to that, so you can actually compile compile to an academic use cell library. Now, there's no point in taping it out because it will be it contain nonsense. It's ghost cells, but you will actually be able to complete a GDS2 tape out using that academic ghost library. So with that, so let's recap. So we went over what the LibreSoft core contains. We described that it has these interfaces, which is memory, interrupts, and DMI only. That the JTAG tap is separate from that, but has a boundary scanner and has its own wishbone master, which is completely separate from the test issuer instruction and data wishbone, so that the over the JTAG tap we can get direct access both to the 4K SRAMs and to the peripherals and test them independently of the core. Then we described some of the differences in the resources that are available within the within an FPGA and an ASIC. In particular, that you just don't have anything existing at all, but also that you have to have this in the GPIO side. You have to have this in, out, and output enable route all the way through to the throughout the entirety of thing per pin on your peripherals. And then we went over the Namigen contributes the ultimately the ls180.v is compiled to Verilog, and Litex peripheral system generates the fabric where the LibreSoft ls180 is a component connected to that fabric, and then you can make the choice to either compile it to FPGA, where the tools will take care of connecting in. IOSIS will take care of introducing you to the ECP5 cells, and on the ASIC side, IOSIS will take care of introducing the cell library, the standard cell library. And by the way, this is where we introduced the black box PLL and the black box 4K SRAM cell at this point. And then told Alliance Coriolis 2 was told about those as well, so that it could actually do the place and route of those 4K SRAM and the PLL cells, which is these tiny little diagrams here, which you can see. You can see them here at this point. This is at the top left, along the top. There's the 4K SRAMs. In that tiny block in the top right-hand corner is the PLL which was automatically placed, manually placed, and so were those 4K SRAMs, followed by automatically placed in route of the rest of the 130,000 standard cells. So with that in mind, let's do a dive into the source code. So the first thing I want to show you here is the pins, the pin banks. All right. So this is one of the auto-generated outputs from the PinMux program, which is very useful to be able to review. Have I got the positions of the the power and ground right? Are they properly balanced and distributed throughout, and so on? But then that's also that then these pin numbers and positions then match up directly with these with the information here. Bear in mind, both these outputs, this markdown file and this SVG image, were auto-generated from the same program. And that program is here. LibreSoft.org Git repositories, the PinMux repository, sources plex plus ls180.py. And here you can see that we've defined the pin banks. There are 32 pins on each side, north, east, south, and west here. And then we define that we actually want on the west side, starting at pin 0, we want 15 pins. So what 6 pins of the SDRAM, which turns out to be address lines 4 to 9. Likewise, then that gets split up here. There's a second split of another chunk of those things. We should actually be able to trace those through. So let's have a look at the west side here. North, east, south, west. Oh yes, look. These ones here, whoops, that is 6 address lines, 84 down to 89 in reverse. Reverse order, because otherwise it would go 4, 5, 6, 7, 8, 9 there. And likewise, you can see these ones here, which go from those. How many did it ask for? 15 pins, starting at number 10, west 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Whoops. You get the idea. Oh wait, I know it's from here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There. Yeah, starting from here. All right. So because in reverse order, it goes from that one backwards. Anyway, you get the general idea. So this program, software engineer, remember, this program auto-generates a JSON file. That JSON file is picked up by other programs, including the LITEX and including the JTAG boundary scan and including Coriolis 2. Okay. So let's have a look now at this is the LS180. This is our integration with LibreSoft and LITEX. Now, LITEX is primarily designed for FPGAs. So let's focus explicitly on the DDR memory interface, the SDR as it's called, right? Here is the ECP5, lattice ECP5 DDR5. So it contains the pins, it contains the, it takes care of the clock, etc., etc. Because remember that the ACP5 has an onboard built-in DDR5, right? Or you can use it to do a DDR3 PHY. So you need to have some way to set up the PLL so that it, etc., etc., etc. You also need to have some memory registers so that you can then program that phi via a DFI, standard DFI interface. Okay. At the pads, once you get outside, and here's the pad list for standard standard DRAM: read address strobe, bank address, address line, chip select, reset, clock enable, on-die termination, and the pattern things. But the thing is that once you have connected to, and you need to you need to tell the bit stream device XPR AC5 how to connect and what to connect to. But once you have connected, said what the connections are, it ends there. Okay, right. So those three wires, if you have an I/O wire, which you will for the data, because that is both input and output. DQ, here we go. Output enables, DQS output enables. So it's directional, it's bi-directional. Once you have that output, you no longer need to track or trace through anything beyond that point. It goes into, as far as you're concerned, a black box. For the ASIC, on the other hand, you are directly responsible for routing the net list through to the DDR, to the DRAM memory, the address line or the data line, the data pad for D0, the data pad for D1, the data pad for D2. And consequently, you need a completely different type of specification for a DRAM phi, because it needs to route those three things. But worse than that, there was a completely separate thing from the pads. The set pads, remember, are separated. Back at this diagram, the LITEX normally would connect these directly from here to here, from the LITEX things to the IO pads. But in our case, because we're doing a boundary scan, and we want that boundary scan to include being able to test the DRAM phi pads independently of LITEX and the test issuer core, we need to separate that. And so this is why back in here we have our own phi class, which is pretty much a direct copy of the standard generic SDR phi. Right, this is pretty much exactly the same code, but here we have these are things. This class is the reason why we had to do this, because we needed in the LITEX code. It assumes that it's buried in that SDR output class, the input, output, and output enabler buried in that class, whereas we need access to, having put those the information into the SDR output class, we need to get at it. To think. So this is why we had to write our own phis, which specifically understand the context of ASIC, not an assumption that it's going to be taken over by FPGA transparent, opaque block, as far as we're concerned. Now, if we have a search for Gen SDR phi in here, this is the Gen SDR phi instance, right? So the way that the LITEX works, as far as an SDR, a DRAM thing is concerned, is that because there are so many different types of DDR memory, they have gone ahead and cleanly separated the phi from the how it accesses the I/O and manages the PLL from the rest of the code, and so consequently you can't pass in the SDR class to the add SDRAM function, LiteX function, and it will connect those and wire those two up for you, right? Things were a little bit different for the rest of the peripherals. The only other peripheral in LiteX which handles it that way is the SDMMC. We had to actually remove the SDMMC because it was SD card, because it was too big to go into the ASIC. But we're still left with that one. Now, in all of the other cases, unfortunately, what we had to do was things like the UART PHY here, and the GPIO, and the SPI interfaces. None of those were designed similarly to abstract out. So we had to literally take a copy of the standard SPI master and GPIO tri-state classes in LiteX and adapt them and just do pretty much a global search and replace substitution, getting those to understand the fact that we needed these triple I/O in, out, and output enable pins to become both in to the things and then come back out again from these class instances, these modules, such that on extraction, so extracting the outputs, we could then connect them to the corona through the through Coriolis 2. And it's where the difference then is that the FPGA, it's a black box. You hand those the triple in, out, and output enable to the black box of the FPGA resource, and you never see it again. Now, here what we also had to do, this is particularly obtuse, is no, not that one. Is we actually had to have an allocator which duplicated, and that comes back to here. These pin pads inside LiteX, we had to make a separate set and a platform resource which had one set which we called core, because it went to the core ultimately. It went through to the code inside test issuer, and the other one was the standard I/O pads. And let me just track that. See, Aerosoc, LS180. So here we define the platform. So these are the resources. This is the I/O resources that are available. Clock and reset, JTAG, I2C, SPI, SD card, SDRAM. That we actually had to allocate a new set of those via a platform, a constraint manager, a LiteX constraint manager, which was if you look closely inside LiteX, you will find that it already allocates an I/O. There's that I/O, so the pad resources. That is a separate resource from the one that LiteX normally allocates. Here is our pin specs thing, which reads the JSON file, sets up some pins, and then enumerates all of them and creates that JTAG boundary scan on a pair. On a per pin basis, it creates a pair of these two, of the pin that has to connect to LiteX, and a pin has to be connected to the I/O pad. And then, unlike a normal LiteX thing where you would just pass that platform resource with the pen definition to LITEX, and it will just get on with it. We need to pass one of those set of pads, and I'm just trying to find it here. You pass one of the set of I/O pads. Here you go, CPU pads. So that's for the DRAM. So you pass the CPU pads to the DRAM PHY, but further down, where is it? Behind the scenes here, when add SDRAM, the add SDRAM, which is a standard function, will get the standard LITEX I/O things, and they are not actually connected. So normally you would pass that through a thing, and it would be a direct connection between the I/O pads here and here. So to get that to happen, you would back here. Where was it again? Oh yes, it's already highlighted. You would not pass self.cpu.cpu pads to the thing. You would pass the self.cpu.io pads thing to the SDR PHY, and that would bypass. Unfortunately, that would, being the standard way that LITEX is used, that would completely bypass the JTAG boundary scan. Consequently, that would make our chip untestable. So we don't want to do that. So anyway, we had to do exactly the same thing for the GPIO, for the UART, absolutely every peripheral. The only ones that we did not do that for was for JTAG itself. So JTAG doesn't try and boundary scan itself. One other thing, by the way, you will know that an FPGA itself has a JTAG interface on it. But that JTAG interface, it is completely separate. So we actually had to have some code. And I'm going to see if I can C4M JTAG. Yeah, here we go. So this was the code that we used from Chips for Makers, and it actually implements a fully functioning JTAG tap interface. So it supports the full JTAG finite state machine of being able to support TDI, TDO, and so on. But what's really nice about it is that you can add these buses, and you can add the JTAG boundary scan I/O that you need, and you can add a wishbone interface, and if you want a shift register for anything else, you can do so. It's extremely smart. So basically, over JTAG, with this wishbone interface thing, we can actually control access the memory through JTAG, and it will stand thing. It's really very, very cool. So let's have a look at what else we've got. So we've got that pin mux. Here's the pin class. Now this was picked up in two places. So remember this, the JSON file. That JSON file contains the pin definition. So it's passed in here as just a Python dictionary. And that creates this class boundary scan, the I/O types of whether it's an input and output or a bidirectional or a tri-stated. Here's your different types that you can have: in, out, tri-stated output, in, out, tri-stated. There we go. Add the I/O that this is creating the boundary scan for you, which you then do in your ASIC. And you wouldn't have this normally in an FPGA anyway, because why would you need it? You know, the FPGA's I/O is assumed to be reliable. It was tested at the factory, whereas but here you can't get away with that. So this is another reason thing. You have to have a boundary scan check and thing on the for an ASIC, because otherwise don't know which bit is broken, the IO pad itself or the peripheral connectivity that driving that IO pad. So now this is test issuer, and test issuer here again, it picks up the pin specs. Again, remember this is the exact same function that we used in the LITEX thing. So this is why it's so important to make sure that you don't end up duplicating this information and maintaining it 4 different places and getting it wrong. So for get underscore pin specs turn, there we go, and that gets passed to the JTAG instance, and behind that JTAG instance will be the DMI interface as well. So we also added via the JTAG interface, we added the ability to disable the instruction wishbone interface. Just disconnect it completely in case there's a fault in the ASIC when it comes back. The wishbone peripheral connection is faulty. Maybe a short circuit or something like that. Also to kind of disconnect the data things, and to disconnect the 4K SRAMs. Normally what you do is you'd have completely separate power lines for each of those things, and then they would just become a big resistor. A tri-stated big resistor, but we decided not to do that because it would complicate the power provision to the chip. So we only have 2 rings, a 3.3 volt ring for I/O and a 1.8 ring for the main core. So here you can see we're adding those black box cells, the 4K SRAMs. That's the ZIX interface for interrupt controller. That's a testing. That's our big main power decoder 2. The source goes online. You can go through it. It's divided up. I think it's pretty readable. Comments. There's a fetch, a finite state machine, an issue finite state machine, an execute one, and where's the other one? DMI interface thing. Oh, and the TB and DEC is its own separate finite state machine, which monitors the control signals coming from the thing. So it noted it only goes ahead and executes the DEC TV finite state machine in between the cycles of the main core one, and that comes back to here. So that's what we're going over there, right? Where are we? Yeah. So this is the function which actually picks up the JSON file and is used by the rest of the code. And this is also used in the Coriolis 2. This exact same code is in the Coriolis 2 thing for it to pick up the exact same JSON file and create the corona. And that corona was this ring here. Can you see there's some lines here? I know those are the I/O pads themselves, but on the inside there's a ring. A thing, and that the positioning of these pads are what the specification was done, which was back in that pinouts program. So it's all computer controls. There is no manual steps involved here. It's quite specific, but yeah. So I think we're good there. So that the main things are you need a boundary scan, and you need the entire code base to understand it, and it routes right the way through pretty much absolutely everything. It needs to be in terms of the 3 pins. To each of the I/O pads goes 3 wires, apart from power and ground, of course. input, output, and output enable. And the difference here there with an FPGA is that it's a black box where the tools, next PNR, ECP5, the place and route tool, doesn't need to know about that, doesn't need to route that back out for you, but instead it sort of disappears into a black box resource defined by the manufacturer of the FPGA. And likewise, you get a different cell library, in effect, which so the IOSIS routing program understands that you have a lot for cells, BRAM cells, DSP cells, GPIO cells, PLL cells, which it is designed to rewrite the BLIF file to correspond to those resources, and that's then picked up by the next PNR ECP5 tool. Whereas for the ASIC, there's a completely different set of cells, MUX cell, DFF cell, as XOR, NAND, NOT buffer, etc., etc. And even massive things like a PLL cell and 4K SRAM cell, you can tell it via by marking those as black box to tell IOSIS, I'm going to deal with this. I've defined this. Please don't try and replace it with something in terms of the standard cells, which we had quite a bit of a fight with IOSIS over getting it to do that, because if we had not marked the 4K SRAM as a black box cell, then what IOSIS would have done was it would have gone, oh, this 4K SRAM is an SRAM. I don't understand memory cells, so I'm going to create a massive set of flip-flops for you, which would have been 5 times bigger than the actual, no, about 10 times bigger than the actual chip. As flip-flops are extraordinarily inefficient way of doing things, but they're very, very fast. So you need them in some circumstances, but because the 4K SRAMs are so big, there's no way that we could do that, or we couldn't let IOSIS do it, and so I had to tell it, treat this as a black box, please. It will be defined by the ASIC designer, who will provide us with a 4K SRAM cell, which then Coriolis 2 is told about and places and then routes the connections to it, and likewise for the PLL. So yeah, I think we're good there. Thank you very much. Questions, and if anybody has any questions beyond these things, you can contact us on the mailing list. Result dev, here we go. So more information about this list here, right? And you can also contact us on IRC, and you can see the IRC logs here, discussions and so on. It's a legal project. This is what you get. So yeah. Thank you very much.
Yeah, ma'am. I think the session has been, yeah, we are done with that video. So if the participants have any questions, please do actually send, please collect all the questions, send it to me. I will follow up with Luke for the answers. So meantime, ma'am, I am uploading the video, the Luke's video into the material today. I will share it after the other session.
Sure, sir. Thank you.
Yeah,
So participants, as Abhinandan sir said, if you have any queries, like with regard to today's session. So please post in the chat box. The same will be like coordinated with Luke Linton sir, and you'll be getting the answers to your queries by tomorrow. So in case you have any queries, please post in the chat box. And Abhinandan sir will also post the link of the YouTube, so you can directly check for this session. So you have time, you have the time of 5 to 6 minutes. If you have questions, any questions, please post in the chat box.
Yeah, this question, which book is best for learning and teaching? Liber SOC is still an open source project, and late a lot of work needs to be done with respect to documentation and especially with the documentation and tutorials. And if you are willing, we can actually work with Luke to build it. So at this point of time, we don't have any book, Ravi Kumar Reddy. So we have to build by ourselves. So this is a more a community-driven project. I would ask the people, any people, students, and faculties, if you are interested, we can create a local group, and we can actually start contributing and build the community.
Abhinandan sir, you're not audible.
Oh, I was not audible. Yeah, I was unmuted. Uh, Okay, so basically, we don't have any standard book for Liber SOC still. So it is driven by community, open source community. And if you are interested, we can actually work with Luke to create tutorials and then documentation for the project, which we can share it across the world. Okay, ma'am. If they don't have any questions, then we can meet in the next session.
Yes, sir. Yes, sir. So, first of all, thank you, Abhinandan sir, for the coordination and the support. And I hope the participants have liked the session. So, even if you want to see this lecture again, so Abhinandan sir has already posted the link in the chat box. Also, the same has been updated in the drive folder.
Yeah.
So, you can follow those. And since you're not having any queries, so we can end the first session here. And we'll start the second session again from 12:15.
Yeah.
Yeah, right, sir?
Yeah, right, ma'am.
Okay, okay. So we'll have a break and again start the session from 12:15. So please, if even if you disconnect, please ensure that you connect again by 12:10. And please know that you are having your second MCQ today from 2 p.m. So kindly be active and get the link ready that is shared in the drive folder. And you'll have half an hour to complete the MCQ that will consist of 20 questions. Thank you. Thank you.
Yeah, good afternoon, participants. Today, now we will have a session. Sir, Shishidhara, sir.
Yeah, yeah.
Yeah,
Is it
you
I'm
can
audible,
start.
right?
Yeah,
Yeah. I will share my screen. Let me check it.
yeah,
Is it visible, Allah?
yeah, visible, sir.
Okay, thank you. Uh, so I'm just going through the UVM based testing for simple synchronous counter and uh, and to explain how the coverage techniques will be taken care. So as well as I will take one example of UVM and I will describe how it can be considered. First, we'll go with that UVM basics, how it will be taken care. So in the Costa sim models, and then we'll go back to the synchronous counter and we'll explain it, how it will be used. Okay. So I'm using a Costa sim here to explain this. So I'm not going to simulate it. So afterwards, after this session, one of my research scholars, Shruti will taken up and show the some of the Verilog commands how to execute in an Costa sim, in a model sim or Costa sim environments. Okay. So Costa sim normally an a simulator which is derived from an mentor graphics. So if you want to do an UVM under Costa sim, so you need to set an environment. So I'm using an environmental setup here. So which is using the set environment command. So with an UVM home, there is a library which is stored all the Costa sim values. So as well as I'm taking the what program I'm going with the Q Verilog options. Initially, I will take the no variable option. So with the null value. So these are all command line commands to be assigned to retrieve all the packages and all the variables of UVM home. So we have an accumulator, we have an increment directory, and we are setting a source file. So this accumulator normally says within your program counter. So once it's setted, so all your retrieved UVM values, unified values, variable values will be accessed through the accumulator values. So then we have an increment directory. The increment directory is a pointer which will be points always from one bit of accumulator to the another bit of accumulator. So that increment directory I'm pointing to the source file which is available in my UVM home libraries. So that is a major library which is used for to access that. Under that we have so many packages to be derived. So UVM home source UVM package.sv. So that is the whole package of UVM. So we are defining here. So UVM home source DPI. So input output DPI, which is with an ACC values. So as well as I'm linking my file here. So UVM underscore basics hello underscore world dot sv. So minus R retrieval values. So these are the two retrieval values I'm taking. Suppress 2167 memory retrieval values. Suppress 2838 29 values. So the simple program for UVM hello world. So I will include the UVM macros.svh system verilog header file. So initially I will declare dut if design under test file that should be an interface. So with that, I will go with the DUT to be defined. So here the major thing is your DUT should be bounded by the test values what you are considering. So normally it will be an a boundary box, so which will be derived uh, covered with all the test cases. So that's why first I will create the DUT itself as an interface which needs to communicate with the test benches, so as well as with the DUTs. So, or in other words, I will say, so it is a linking bridge model between your DUT to the test bench. So that, so what all the content which is derived from a test bench, so it should be evaluated at the interface and taken to the DUT. And again from the DUT, what all the vectors or what all the responses it will be generated, it will be taken to the interface, evaluated, and put it onto the test bench to generate the next test vector. So now as I am not having any logical value here, so that's why I will make it blank of both the module and the DUT values. So my interest is to this, you already known it, so that's why I'm not going to describe it. So I will show you the another one example here. So how your DUT should be used for an UVM categories. So I will go with declaring the UVM. So from its UVM packages, I will declare a class environment. In that class environment, I will take up the UVM basics. So you can see there. So I have declared an package here. Package. So I am ending that package, end my pack, right? So under this package, I am declaring all my UVM or my test environments, what I want to consider under an UVM. So I am declaring two environments here. One is a test environment to access all the test values, declaring from in a tree-based structure, parent to child. So and child to a parent also. So and similarly in the test cases, I'm declaring all my supplyable or generatable test values to my environments. So two environments I'm declaring here. So now first we'll go with the my environment, which is extends with an UVM environment. So that is the name it will be given. So before that, I want to say to import all my packages, UVM packages, import UVM underscore package. So which is imports all my package values of UVM techniques and derive to the environment which is derived, which is defined. So here I'm defining two environments. For all the two environments, these package values should be imported. So from where it is imported, already we defined that here. So UVM package.sv. From there, that source file, it will be accessed. So to here, UVM package.v. So my environment extends UVM underscore environment. So UVM component utilities. So all the utils which is present, which needs to be considered. So will be declared in my environment. So that's what I'm taking as a component for my UVM, and I'm going to declare all the values, all the environmental values over there. So function new. So as I want to declare an hello world. So I will take that hello world as a string. So which is a parental value. So under that, what all I will return, that will become a child. So if you are writing a two components, let us say I want to declare a half adder, full adder using a two half adder. So the full adder will becomes the parent and two half adder will becomes the child. So at that time I will declare so the function as an the parent function as an UVM component parent as an it's a parent function which will be considered with the logical values. That here I'm taking it as a string name. There you can take it as a logic IO values or logic input values, or if you're defining it structurally, so then you need to take a structural elemental value over there. So then I will declare my calling values super.new name. So name is given and parent as an parent only. So I will end this new. So and if you're writing it parent to child, the first parent should be declared. So after this, we need to give super.new name comma child1, super.new name comma child2, etc., etc. How many childs you have? So in a full adder using a two half adder. So then we need to use so the parent as a full adder and child as an half adder and an half adder. It's a tree structure, right? So it will be built over there. So now, so for this parent or this new, so we need to construct so what are all the face UVM face values you want. So the face values means you declare an test vector. So you declare an event for the test vector. You declare a time for the test vector. You are given a constraints constraints there. So all those things used to be given over there. So once you are given, it will be taken it as a building function and builds for that given face value. The face will be a constraint file again. So with respect to that, I will write function. So and always once it's built, nothing to be written. So all the netlist will be stored in the given file name only. So from that file name you can take to so what objectives you want to learn, you want to run on that given constraints. If I say if you want to run a clock, so you can take a clock. If you want to run the input A, you can run the input A, etc., etc., etc. So I will build super.build face. So I will function void build face. This is the name of the file. UVM underscore face super.build underscore face. So this will be building. So the total value of your constraint or the values which is used to be retrieved to explain your UVM functions. So and I will end it here. I will build it the total value here. So if you are having a 3 parents and one parent and 2 childs, and you want to define different constraints for all those things, so then you can define build phase 1, build phase 2, build phase 3. So and build phase 1 will take the constraint what you are defining under a phase, and build phase 2 will define the constraint which is defined using a phase. So and similarly for build phase 3 also. So now, so each phase can have their own constraints or own UVM parameters which can be run so in a different values. Task run phase UVM underscore phase. So this is a declaration. I'm calling it as a task, a single task. So I'm using the UVM phase value which is declared over here, UVM phase, right? The phase only. I'm retrieving those values which is stored over here, the phase value. So and I will call so the phase dot what you want. So if I say rise objection this, so T to be a capital, I'm taking there. So this, so then the total value will be written there in an objection and it will be retrieved. So let us say, so I want to take an rising edge of the class. So then I will say rise underscore objection clock. So that clock will be taken rising edge of the clock. So if I say fall underscore objection clock, then it will take an falling edge of the clock. So similarly, what phase of values you want, so that can be taken. And whenever you raise a phase or whenever you access that value, so you need to show it as how many times that access value to be there. So normally, so this will be taken care with your timing parameter. That is a delay parameters. So how much delay you have and how much delay you are taking care. So etc. 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 So here I'm taking and 10 nanosecond delay. So with respect to the 10 nanosecond delay, I'm raising my clock. Let us say here this. So and after 10 nanoseconds, I will go to drop that value. So that is the total value will be returned within a 10 nanosecond values. So I will end my task. So this is the total task which is defined. So if you have n number of variable, so n number of variable which needs to be accessed, so then it will be goes with each value with that appearances, and you can create n number of tasks also to run this. So to show how each UVM parameters will be taken care. So this is my UVM design environment or declaring an environment. So the same environment I will utilize here. So to test my values. So I'm declaring the same. First, I will call my class. My test extends UVM underscore test. So the same declaration what we done there. We are given extends. So with an UVM environment here, I'm taking the file name as an my test with the UVM underscore test. So I will take all my utilities which is present in my library, that is which is declared. So here uvm.updpi. So the same values I'm accessing with that. So including the packager values also, right? So uvm underscore test. So uvm component utilities. So my test. So my environment. So this is total utilities which will be accessed to my test classes. So my environment H. So what is my underscore environment? My underscore environment is the declared environment here. So all my values which is declared here. So I want to test that value. So that's why I'm calling so my environment. So and I'm also calling my environment underscore H, which is an header file, which is needs to be accessed. So for each value of my environment, I will take here component UVM component. So here we declared that as an a UVM component with a parent, right? So I'm calling the same one UVM component parent super.new name comma parent. So now this function, so from the my environment will be utilized with this component value. So it will be combined. So function void build phase. So now the same build phase I'm taking to build my test vector. So now I'm using the same build phase, so which is declared here. So through calling my environment values. So I will give for each phases. So with their task value by defining an ID, type ID, and every time once I executed this phase value, I will create my environmental values. So let us say I have three values which is declared under this parameter. So then I will go and access all the three by creating three IDs. Type underscore ID1, type underscore ID2, type underscore ID3. So or if you want to check for three different values of the same parameter. Let us say I want to check the clock for three time values. Let us say 10 nanosecond, 20 nanosecond, and 30 nanosecond. So what I will do, so I will create here the objection. So and each objection I will call as a type value. So type ID underscore ID1, underscore ID2, and underscore ID3. So and each time I will create my environment. So through by calling my environment underscore H for my environment and the value. So here I'm taken this value. So there I will take clock 1, clock 2, and a clock 3. So each clock so will be runs for the given time period and shows us how it will be evaluated. So for a build phase. So this is for my test classes. This is for my environmental classes. So this is my total package, so which is declared. So for my values. So now we need to combine those two, right? So we need to make a total bundling of your test bench to your DUTs. So I will take module top. So import UVM underscore package. I will call total packages to be included. So as well as my package, right? So where the my package is written. So my package. So we are declared as an my package here, right? So I'm importing the total package over here, both the things. So that I can combine. So I will say DUT if one, I declared the DUT here as an a DUT if, right? So I'm naming it as an a first DUT. DUT if is then modular name which is declared. So DUT if one is then calling modular name. So similarly DUT1. So what is the input or output which is declared here for a DUT? So that is DUT if underscore if, right? So I'm calling DUT underscore if one. So for if values. So which is so interlinked over that. So initial begin run test. So I will run my test value. So run test. So my test. So where is the my test? My test is a class which is declared here. So under my package, I will call to run that test, right? Run test is a command, library command. So it will be runs. So those total values. So if I execute this, the total values will be executed. So in my macros, so I have another one detailed parameter. So let us look at on those appearance. This is the same. This normally we declare the same thing for all my files to be accessed, right? So this is my complete source file. So including UVM macros.svh. Now I will declare my DUTF, right? So this is for simply return to test some of the memory values by writing and reading with an command values. So one memory file, what we return. Okay. So I will call the interfaces. So normally the interfaces will have the clock, reset, command line, and address and data, because it is just works as a buffer. So that's why I will take only those values. So clock, reset, command, address, and data. I will take address and data as equivalent as an 8-bit values. So this is my DUT. I will import my package UVM package and UVM underscore package. So always posits underscore if dot clock. So this is a declaration. So my clock will be named as an underscore if dot clock. So UVM info, I'm giving the info what to be done. So always the DUT will receive the values which is declared or which needs to be accessed. So as I'm having to interlink these values, interface values to my DUT, so I'm just interlinking those two. So DUT received command, address, data, right? So where the command should be combined. So command should be combined as an if dot cmd, if dot addresses and if dot data. Why if? So because I declared my DUT as an if values, the variable as an if value. So that's why where and all I will call a variable, I will use if values. Okay. So and I will say so non-returning values. So such that UVM none. So now I will declare my transactions. So and then I will write my test cases. So I will go in brief with this. My sequence library ran a package. So import UVM underscore package class my transaction extends UVM sequence item. I'm taking 1 by sequence item. So all my transaction taken to utils. So all the utilities will be assigned with my transaction. So what are the major commanded major 3 parameters? One is a command, address, and a data. I'm taking only that 3 command, address, and a data. So as these 3 are needs to be accessed randomly, I will use the rand. So which generates the random variable values to these commands. CMD, address, and data. So as address and data will be an integer value, I will declare all rand values as an int. So the CMD is a bit value, so that's why I will call it as a bit. So I will write my constraints now. So what are all the constraints you want? You can assign it here itself. So I will take C address, C data. What is C there? So C should be explained. So with a signal which needs to be mapped to so these values if underscore CMD, if underscore address, and if underscore data. So I'm just calling it as another one constraint addresses constraint data. So I will say address can be from 0 to 256. Our data can be from 0 to 250. It's only the 2 constraints I'm giving. So if you have a clock constraints, also you can give constraint C underscore clock. So the clock variable. So clock from 10 nanoseconds to clock to 250 nanoseconds. Something else you can do. So here I'm giving it says an integer value. I'm declared as an integer value. So I'm giving from 0 to 256. 0 to 256. So I will take a new, the same string name. So null value. So I will return that value. So now I will go with the conversion, converting to string. Right, these are the data value. I want to convert it to a string value. So this is the bit value. These are the 2 decimal value. I will call and I will print that. Convert to string function. So do copy. So I will declare all my objects which is needs to be called for my transaction which is given here, for the given transaction here. So to my UVM files. So that's why I will call one value which is I'm accessing here as an one object values. Okay. So each object so needs to be compared and proven to the given address or specified address, or it should be mapped to the specified address. So that's why I will take it as an normally as an the RHS and LHS value, because I want to go with to prove that. So that's why. So if you want, you can give your own name, no problem there. So RHS. So my transaction RHS underscore super do copy RHS. So I will make it to copy and store here in the name file. So in the string, right? So every time I will check it out what my values, UVM object values will be run through. So that's why I'm seeking that through my cast variables. So RHS underscore dot CMD, RHS underscore dot address, RHS underscore dot data. I am taken that as and defined the 3 variables. I will take the 3 variables and I will map all the 3 variables to my variables which is declared. So I will take all the object of transaction appeared here to the CMD. So let us say CMD will become 00. So I will take the 00 to the CMD. So here the address will vary from 0 to 256, any value which will be mapped to the address. Similarly to the data. So I will just copying the value which is our transaction appeared. So in these 3 values to the CMD with respect to this objectives. So with respect to the constraints which is defined. So let us say if I am address is crosses to any 257. So if it is crosses to any 257, so then the total address will be mapped to here and it will be says an error. So because your RHS will not map to an address, because your address is from 0 to 256, which is not tapped. So it will use an overloading errors. So because it is crosses to the assigned data values. So now, so after assigning it, I want to compare it with the assigned RHS command to an CMD command. So this is only to seek. So what all I taken a value or assigned a transaction or appeared a transaction is equivalent to the assigned constraint or not. So every time I will check the objects and its value with the UVM object, and I will make a comparison by calling a package UVM underscore compare. So I will take all the transactions. I will seek all the transactions. So and all the transaction I will expect to be the status 1. So that's why I will declare it as a status parameters, or I will store it as a status pointer values also. So I will call a function super dot do compare this function RHS and a comparer. So for every transaction. So because I am casting it, so there is a transaction, that transaction will be go and take from there. So what are all the values it should be compared? So we need to list here. So as we have only 3 signals, I am comparing only the 3 signal, CMD address and a data, comparer data compare underscore field, comparer data for CMD. So what you need to be compared? This is storing value. So what you need to be compared with CMD and RHS.CMD. So CMD is here you are assigned from an RHS for an previous transaction. So now you are making a transaction now, new transaction. So that transaction will be taken and compared with this. And every time comparison will be results to another bit value. So because that bit value will be stored with a CMD, and that comparison, if it results with a logical one, then the status will be set. Otherwise, the status will be reset. So the address, similarly, the address and RHS address. So again, the address will be taken, compared and stored. Data So data RHS and data will be taken, compared, and it will be stored. So total status for all the three, the status 1, status 2, and status 3. So I'm not naming it because the status 1 with an address pointer I'm taking care. So that the total address array value, address value should be, sorry, the total compared value will be stored here, and it will be returned through that status. So to your return function, right? So this is a total UVM assignment. So if you are going for to make any utilities to modify with respect to the transaction, so or with respect to the comparative result you are obtaining, so then we can write that modification also by taking the sequence with the modifying statements, read, modify, write values. So each time I will call an utilities, UVM object utilities. So read, modify, write. So there is a function string name, super.new name, end function new. So I will call my task to do that. So this is the total task body. So what are all the variables I will declare for my transaction? That is one transaction which will be taken. So I will take two transactions here, A and a B, sorry, A and a D. So which is mapped to, so all my variables which I am checking, or all my data which is declared, so need to be checked. So I will take the objection. So that may be a constraint which is defined, right? So with creating it, it's the same what we declared. So I will start the item dot tx. So I will assert the value tx dot randomize. So once you are asserting, so it will check all the transaction which is appeared. So as I'm using a randomize, so whenever there is an event, the transaction occurs, that will be in a randomized values. So all the transactions will be stored with an given appearance true values. So if it is the null, if this results with a null value, so then so it is also resetted to that transaction. So or if you are taking some signal to make it as an true value continuously, because in some of the cases, if I say reset, if I am using, so the reset, I'm evaluating all my logic with respect to a reset. So I defined the reset as an logical event to evaluate my circuit. So at that time, I will make the total transaction or as a static transaction as that reset pin as an illogical event. So here my CMD pin should be an logical high to access the address and a data value. So that's why I will making my transaction as an logical event. So finish item transaction. So start item to and finish item I'm taking and I'm asserting. So those values. So as I told, I'm taking a two variables here, A and D. So I'm assigning the A and D for the transaction, transaction.address, transaction.data. So both will be taken to A and D. So as the address is a constant value, so and data every time is goes on increasing. So I will increment the D value, plus D value. So or you can do D plus also post or a pre-increment, you can do it, no problem with that. How you can take that is left to the parameters. So I'm taking the plus D, so which can do the pre-increments to the system. Transaction, my transaction. So I will create the transaction for A and D now. So because I'm created transaction only for CD now, sorry, CMD here. So I will create the transaction for A and D. So I will start the item for the transaction. I will assign the transaction value. So all the transaction of address through the A, all the transaction of data with the D. So the CMD we already assigned with 1. So again, I will checking and I'm making out it as a 1. So and all this transaction what I am taken, so will be taken to your test cases. So that's why I will make UVM underscore test done dot drop underscore objection this, right? That is the end modify. So now you can check your transaction also. So with respect to an sequences, sequence commands, sequence of commands, 1 second. So you can have how many constraints you want for your sequences. I am taking 3 constraints there, 4 to 6 I am having 0 to 7. So in that I am assigning a constraint for 4th bit, 5th bit, and a 6th bit. So where? So I am taking it inside to that. So only those parameters. That's why I'm given how many constraints. So this is simple, the same as the previous one. So we can declare. So now I will call. So the right sequence to modify. So and I will create a sequence, start item and a finish item. And if you want to create a sequence also, you can give it. Let us say I'm using a priority encoder. I want to create a sequence to encode my data. So that sequence you can create. Or if you are going with some of the coding generators. So at that time you want to create your own sequences to test the data. So at that time you can create your sequences here, start item sequence. So you need to give that what sequence is equal to. So 1 1 1 1 0 0 0 0 something else. So you can create. So with respect to time also, start item sequence at 10 nanosecond. So the sequence will be so 1 1 1 1. So at 20 nanosecond, the sequence will be 0 1 0 1 0 1 something else. You can create your own sequences. If you are not creating, it is automatically take its own sequence, default sequences. So at that time, it maybe pushes to the infinite loop also, because it's go if you are written n number of bits, the probability of taking the n number of bits may be very high. So in the network communication, or if you are doing any communication protocol testing through an UVM, so you will create the sequences with respect to the variable. So let us say I want to do it with respect to an AHV buses. So I will take the AHV buses and I will assign the input values. There will be an data input of 8 bits, 8-bit input values, or 16-bit input values. So 2 to the power of 16 combination it will take. Now here I'm taken data as an A as an 8-bit, D as an 8-bit. So address as an 8-bit and data as an 8-bit. So that it will take first 2 to the power of 8 for address and 2 to the power of 8 for data bus. So both the things. So it will generate that sequence and it will take to the test bench sequence of commands. So importing the packages. So this is my package, total package, what I am defining it. So type def UVM sequencer. So my transaction, so sequencer. So I will take the driver to access this. Okay, so what all the driver you want, you can take it. So I will declare all my utilities for my driver. So you can make it the virtually your DOT and testing DOT as well as the virtual DOT. So which can be the DOT can be an virtually appearable if you are doing a black box testing. So if you are doing a white box UVM method testings, then it will be a direct accessing. So I'm doing with an black box, so that's why I'm doing virtual DOT underscore if DOTVI. I'm not written DOT here. So think that DOT is a string which is declared to say hello world. So that's why I'm not written this. So it is a default understanding there. So function new string name UVM component parent. This simple where we declared in the previous case also. So now, so we done in previous case super build phase 1. I told you can give the phase configuration there. So I'm giving a configuration there. So by asserting it. So what configuration I'm giving, what signals I'm taking, so what values I'm taking, so I'm declaring here. So I can't do all the parameters under my DOT because it may changes its configuration. That's why I'm created an virtuality here. So that virtual DOT I'm calling virtual DOT underscore EF. So get the variable value. So this is I'm given as a constraints there, testing status value. So and I'm putting to a DOT underscore VI. So what all the values you want to include into this, so you can declare that. I'm just saying DOT underscore VI, right? So task I'm running now, the total task. So I will take the transaction, CMD, address and data, and I'm assigning to my DOT virtual values, right? And then I will go for looking at the values. So this is a simple monitor command. So where and all you want to monitor, there and all you can take the parameters. I'm directly going to an face building block where I will say the port values. So I'm declared the port values here. UVM analysis port. So what port you want to analysis, you can take that. So let us say here I'm analyzing address and then a data port. So I'm taking only the transaction of that. So I'm assigning that with an this, because this is a status which is taken care for address data and a CMD, which is declared in the above function. So that I'm taking here. So and I'm configuring again virtual DUT with respect to this A port values. So then I will run my transaction CMD address and a data. I will write the transaction to my port also to write the values. And now, so this is an optional case. So if you want, you can do it or you can omit it. In some cases, if you want to check every transaction, so with respect to their value assignment, so then you can declare it as an agent. So and every agent, so what you are declaring needs to be considered with what port assignment you are doing for address or for data or something else, right? So now I'm taking care of all the values to monitor here. So I will declare all my sequences for which is assigned with the A port. So here I am taking A port for all the three values. So that's why I'm taking here. So now what all the parameter I want to monitor? I want to monitor the sequencing. I want to monitor the driver which is assigned. So and then I want to go with the monitor. So in the sequencer, I taken the sequence what I want to test, right? So for address and the data. For driver, I'm checking so what all the values will be transacted. So in the monitor, I'm checking. So is it the values which is assigned are taking or not from both sequencer and driver. So that's why. So I'm assigned all the three values. So then we need to go with subscribing it. So the values. So what expected you can have. So this is again an optional case, cover underscore but sample. So if you are doing a coverage analysis for these transactions, you can use this. Otherwise, you can leave it on this. So here I'm doing a coverage analysis. So that's why I'm taking the cover underscore bus samples. So my transaction expected new, expected at copy. So all the values, all the expected I'm taking here. So to an expected variable. So all the transaction which is taken care. So and if I will compare now, dot t compare is to an expected to the values. So you though both the new and an expected is compared. So if both are different, so then I will display an error. Transaction differ from expected. This is the displayed value UVM dot underscore error as an error. So you can pass there also. So else if you can write so UVM underscore successful. So the variable name transaction is successful. So similarly, so you can, as we explained, you can create an environment also for each transaction, and you can make out the each environment analysis. So I'm taking the environmental analysis here, type higher severity action here. So this is not, it is the advanced cases which will be taken care. So for now, so we don't take this to explain. So that is with respect to simulation phases, every simulation. So I'm going on displaying with respect to the log files, and I'm reporting all the severity actions. I'm noting it in a file, and whenever I want, I can go back and I can check it out. This is a normal test bench which is created. So for the create the string values, right? UVM underscore face, super dot build underscore face UVM resource DB virtual. I will read the name from the original DUT to the virtual. So and I will make an comparison. So if both are fails, so then no virtual interface is set. So if both are setted equally, so then we'll create an environment for them. So what environment you want. So that is through a configuration values. So you can set the commands also, what all the agents you want and what all the things you want. So I will setting a commands for to sequence to randomize because my sequence contains address, data, and a command value, CMD values. So that's why I will set a request for that. So in the request, you can give constraint also. So that constraint is left you have can give. So because we have given a constraint there, I'm not taking care. So if you are not declared that, you can give the constraint in the test bench also. So in some cases, if you are using a multiple clocks, so to stop some of the clocks or to hold some of the clocks, so we are giving that constraints values here. So that is a temporary period. So what we are giving. So this is the main file, so which is accessed. So I will taking the duty if reset one. So negative edge of the clock. So I'm running it totally, right? So again, I will call resource underscore DB and I will finish on completion of one. So run the test. So iteratively and test the values. Okay. So this is about the UVM. So let us go and see. So I will just take another 15 minutes to brief out this coverage analysis. So I will not taking all the coverage parameters, some of the coverages which can be done. This is the some synchronous 4-bit synchronous up counter which I have, which we designed, and we are testing all my coverage analysis for this. So Q02 and a Q3. So synchronously it is working with an J flip-flop. So this is the setted clock values are setted working principle or a truth table which is defined for those values. So you can see that first clock pulse I will take all low, so the output is also low. In the second clock pulse I will set it as an high, so Q1. So I will say there is a toggling, so I want to check this toggling, I want to cover this toggling, right? So in the third clock pulse I will not check anything. So in the fourth clock pulse I will check two coverages. One is low and condition is not satisfied, high remembers. So similarly I will go and do it up to an 16th clock pulse because I'm generating an 16 values. So I run it through an this one also ADA playground. So this is my total appearance. Similar to that, you can check it out. I am declaring an interface clock select data. Data is 4-bit, 3:0. So I'm declaring a positive edge of the clock, input select data, end clocking, end interface. So UVM package I'm calling, importing. So I will also including the macros, sv.svh. So class myConvert extends to UVM components. So I will calling my file or my class file, myConverter. I will making virtually my interface underscore if. So what all we have explained in the previous files, I'm utilizing it. UVM and utilize my converter, cover group, my CG, my CP cover point, if dot CB is my clock, right? Data if CB select. So select is the another one variable what I have. I will make the parent as null because I don't have a parent here. So that's why I will call it as a null. So name parent, my CG is equal to new. This is my total design file, so which I called with a string value. So task run phase. So I'm not declaring any constraints here. I'm omitted all the constraints here. We explain you people. So with the constraints, I have some other file which can be run through constraints. So I'm not taking care of that. It requires more time to explain how to give the constraints, how it will be taken care, how it will be evaluated, etc., etc., etc. So that's why I'm not taking care. So if you want, you can go through the reference modules of Accelera for UVM or OVM methodology. So he will explain how it can be given. So task run underscore phase, UVM phase forever begin. I'm declaring my transaction here to run. So with an run phase values. So this is my total test bench code. SV unit defines dot svg import sv unit underscore package. So which is a package which is included. with the unit underscore text. So module my underscore coverage unit test, my module name I am given. So this is a test bench. I am not declaring any IO. String name my converter utility. So SV unit test case SV unit. So my converter duty, I'm not declaring the duty over here. So I think that the duty, you know it. So that's why I'm omitting the duty here. So I'm just say duty will be there. So within my converter, I'm attaching that my converter over here. I'm not explained anywhere else the duty logic. This is my only a general design file what I have. So for the UVM declaration file, that is. So logic lock, logic select, logic data, my interface. So I will take my interface, which is declared here as a class, my interface if, right? So I'm calling that. So function wide build, SV unit underscore UT, new name. So I'm taking the designed value. I'm calling the designed value. So here I'm calling it new. So that same new I am taking here. The same new I am taking here. New. So duty, my converter, type underscore ID, create duty null. So I'm not giving any value. I'm just calling the duty. So if you want to give any constraints, you can give the constraints there. So in the file, and you can call that constraints over here. So I'm taking null value because I don't want to push more constraints to my counter. So that's why. So duty dot underscore if my interface. So task setup. So I will set up all my environment now here. So SV unit underscore UT dot setup. Setup is again library function. So before each test, we need to do this setup. So, and I will say what all the initial coverages will be there that can be covered over here. So, and I will say all the coverages which is to be stopped. So I will take the stop signal to stop there. It will be starts here and stops here. So if you want to give a delay for that, you can give that. So and I will again clear the interfaces so that I can go for the next one. Clock 0, select 0 and data 0. So whenever you don't want to, you want to come out from the test. So if I'm, let us say I'm using an 4-bit, it will goes to n to the power of 4 combination. In middle, I want to tear down. I will call the tear down function. So it's a tear down function. Or in some cases, in real-time testing cases, we will go for n period of testing. So at that time, in some cases, I want to tear down my testings in somewhere else. So at that time, I will use the tear down function also. So now I will take the signal to toggle and explain it how it can be taken care. So toggle interface pins, check that all coverage is set, select 1. So I will take my signal select and I will assign it as an 1. So because it is a one signal, so which needs to select my counting values. So for int is I is equal to 0, I is less than 16, I plus r equal to 1. So incremental value begin. So data is equal to I. So all the data is assigned, it will be taken care. Toggle clock. So toggle clock. If I is equal to 7, so fail unless, so I will take up to an defined coverage value. So half of the coverage should be hit. So because I'm taking 16, 0 to 7, I will take. When attain set on a 7, so I will say half of the coverage should be hit, right? So and again, so I will take to 100. So after completing this, right? So I will come out and I will say full coverage is done. Okay, stop coverage class. If you don't want at the end, you need to stop that one. So we'll disable it at the end. So toggle clock, repeat clock is not this clock generator. So dump the variable because I'm using an normal function mentor graphics tool, as I told. So first sim. So that's why. So in the EDA log, I'm going with mentor graphics tool. So that's why I will use dump variable. So the dump variable name is this one. Should be given. So this is the simple counter. I'm generating the counter. You can see that. I think it's not visible. So here there is a counter values is there, so which is taken care. So if you have any doubts regarding this, so you can just ask me. So I will clear that. Afterwards, I will hand over my session to my research student, Shruti. So now I will hand over my session to Shruti. So she is my research scholar. She's doing PhD under me on NOC verification techniques. So she will take care some of the programs in EDA tool, how to do it with EDA tool and how to do the system Verilog program execution. One or two programs she will explain and show the simulation also. With respect to that. Okay, thank you.
Good afternoon, everyone. Am I audible? Yes, thank you so much. Okay.
We will take up the questionnaire at the end after this. I have one question there. I will take up at the end.
Okay, so this is I'm Shruti, currently working at the National Institute of Engineering in the Department of ENC. Uh, I'll be presenting a very simple program that's a counter program by using the basic constructs of system Verilog so that you will be able to map the basics that you have gone through till date. So here I'm using the online tool that is the EDA Playground, which is open source, and you have various options over here. I'm sure most of them might have explored over this. So here in this tool, as an introduction to this, first you need to register yourself to make an basic operation to work here. Followed by you can select the design that you would like to program for. This not only supports system Verilog or Verilog, you can also have Python, Perl as well as VHDL with it. You can also work with the simulators that you have. Most of them are licensed, but here you can have the emulators for certain tools over here. I'll be using Mentor Questa. The problem here, most of them for Verilog, you can use IITR Verilog, but thing is that there are some constructs which IITR doesn't support of system Verilog. So that is why I've selected Mentor Questa over here. Then if you want to see the waveform that comes as a result of the operation, that is a simulation result, then you need to enable your wave. And then after the run. Okay, so you can even download the files for your future use. So coming to the program, what we have written over here is, so this is a tool where you need to have the design as well as the test bench written. So we have written a simple counter program, which is an up counter, but by using a data type which is called as the dynamic array. Okay, so how do we define the dynamic array and what are its features? First of all, when you write any program, we are going to define with a data type which is called as logic. Okay, this is an 4-state data type which will take the values of 0, 1, x and z. So the data type matching plays an important role when you're writing any basic system Verilog code. So here we have used logic. Apart from that, we have 2-state data types as well, which belong, a few of them are int, bit, okay, which we'll be seeing in the next another program. So we have defined here a dynamic array, and the syntax from which you can identify is with this square bracket with an empty space. Okay, this defines an dynamic array. So now where will the location be allotted for this dynamicity is during your runtime. So initially there is no space allocated. So the advantage of having an dynamic array program is that the simulation time will be reduced, where because the allotment of the space for the arrays will not be done at that point. So when will it be allotted? Once the simulation is done. So that is during the runtime. Okay. Then how do we define that the space that you need to give here is that, so you're going to initialize the array with a command which is called as new. Okay, and you're going to write an initial content here because you are going to initialize it once. Okay, so that is initial. So this is the way name of your dynamic array, that is dyn I have defined. So new 1, that is you're allotting and 1 element space for your dynamic array, and then for that space you are initializing with the value 0. So that element is getting initialized with 0. Okay, followed by, we are going for the operation, that is the counting operation that has to be done. Okay, so when you're going for that, so we are going, this is an asynchronous counter program. Okay, here when the reset is 0, you are going to have the value 0, else you are going to get it incremented, and after every increment is done, you are going to allot, or you are going to put that value into the variable c, which is actually your output. Okay, this program to be run, we are going, this is a device that has to go for testing right now. So the device under test is count. So for that, we're writing the test bench program over here. So in the test bench program, you are going to initialize, or you're going to declare the variables, that is the clock, reset and the out, followed by your, this is the device which is going for testing, that is count. So the module here is count, so that is what is the device here, count. So we have written it in the same format as per the input and output, so that it maps. Then we are going to give a clock with a delay of 5 units. Since we have not used any time scale, so we are not going to tell it whether it is millisecond, second or any unit. So it is just as 5-unit delay. So how do we go about it is, initially we are going to keep it as 0. After the delay of 20 units, we are going to make the reset as 1, wherein the counting will be going on and the duration will be for 150 units, followed by, when the reset, after 150 units, again you're making the reset 0. Then after the delay of 20 units, you're going to make the reset 1, and you're running the simulation for another 200 units delay. And then you're going to finish the program, or you finish the simulation. So now how will this file be available? All the changes, whatever you do needs to be given to the simulator with the file which is called as the VCD, that is the value change dump. Okay. Now what will this dump.vcd have is all the changes that has taken place during the simulation will be stored in that dump.vcd file. Now these variable, and then with the function of dump values, you are going to be able to obtain all the values that were changed. You will be able to view it, and that's how the simulation, your test bench is going to end. So this is an command which can be written at the anywhere beginning as well, need not be at the end. So this initial part, this of the value, that is a dump file part, can be written anywhere in the program, that is before the always block as well. So we are going to run this program by just giving run. So when you run it, that's how your simulation is going to look like. Okay. And by looking at this, you can see there are two stuff that are two times it is getting repeated, one with respect to the your design, and the other one with respect to your test bench. Okay. So but the result is the same, the variables are different here. That's why I just need to show that the values were the variables that I had declared, the values are different, but the positioning were the same. That's why we can see that. Since this is the program that I have written is an asynchronous one, you can see that asynchronicity is obtained at the reset, enabling of the reset. Okay. So as soon as the reset pin is high, irrespective of the clock, the counting is begun, that you can observe it here. And the are going along with the clock. So you can see the duration of the simulation here with the time scale. Since any of the time scale is not precisely given, so it is randomly taken. And that's why I've used the word of units and not specifying any particular time scale. So we can change, we can see the changes by going for an synchronous counter program over here, by just giving a synchronicity for the reset that works along with the clock. So when I run it, you can see here with respect to the reset, no matter where the reset is enabled, you can see that at the positive edge of the clock itself, the counting or the counter starts to count and the simulation goes on. So this is a simple up counter with using the features or the data type of a system Verilog, that is the dynamic array, where the values or the location for the allotment or the dynamicity is done during the runtime. So what will be the advantage is that the simulation time, if you could, here you cannot analyze the simulation time in detail. That would be better if you would go for any licensed tools like the Xilinx or even with Cadence. the timing analysis would be more precise. So if you observe there, we can see that dynamic arrays will take a lesser time compared to the one which are fixed. So here that analysis may not be an most accurate or the precise one. There is another program here which I would just show it to you on, which is going with an fixed array. That is, you are going to have the fixed count, that is of defining the size of your location, that how many bits. Okay, so that is 3 down to 0 of a 4-bit count. We are having an intermediate register that is 3 down to CC, that is also 4 bits. So logic is the one which can be used, which is going to work or which is going to be similar to an REG, that is a register variable, which you have already used. So this can be interchanged with REG, since REG is also a 4-state variable. Now, here, if you see in this is a simple program where if the reset is 0, you are going to assign 4 bits of zeros to the counter, the intermediate register. Finally, else if the value of the I, so we have declared an int I over here, the value is going to be less than 16, then you are going to increment it. Okay, you are going to assign the value to the location, and then you're going to increment the index I, and then finally you are going to assign that to the out, cout, that is the output variable. And the same thing, if you want to call this entire program onto any test bench, then you need to just replace the device which is going for testing with the variable that you are going to, the module that you are going to give. So if you change that, the device that you're going for testing will be called inside your test bench, and the simulation will be done and the result will be obtained. So this is just an introduction or a simple, this is just a simple program of counter using the basic features of system Verilog. Okay, there's a question that says in the design code we write initial, in the Verilog code we don't write initial. Please explain this. In Verilog code also you can have an initial written, okay, but the difference with initial is that if you are executing anything only once, okay, then you are going to have it as an initial. The always statement that you write, it is doing the operation continuously as and when the variables that you declare after writing that always at, okay. So whatever variables that you write over here, as long as the things are changing there, the operations that you write inside the always block keeps doing it, or it keeps executing it. But what with the case of initial, it's just that it's doing it once, okay. So in Verilog also you can have it.
And another one question. The dynamic arrays, what you are declaring may not be synthesizable. In some of the tools we have it, but in Cadence we are not working out with the synthesization over there. We need some conversion. So only for verification we can use it, the dynamic arrays. For design elemental values we can't use the dynamic arrays. And another one question is, what is the suppress and the number used for? So the suppress is a command which is used in UVM techniques to declare the total simulation monitoring timings from that unit values to the another unit values. The number is the unit values which is given. So normally it is a library component value which is retrieved so from that unit values. So let's say if you are declaring a monitor command $monitor, so we need to see that monitor command where it will be declared. So those cases it will be taken that suppress. So or you are having some constraints which is run out. So those constraints can be used to or utilities you are using. So how many utilities you can go for. So those things can be declared under that suppress libraries. Any more questions? If no questions, Abhinandan, we can wind up, no problem. Thank you. Abhinandan? Dear participants, so again, tomorrow there will be a session. You join at 10 o'clock as usual. Okay, so now today's sessions will be winded up. Thank you very much for attending. Thank you very much.
Thank you so much for attending and providing an opportunity to
Thank you.
Thank you so much.